All right, so this is a speaker cone that I use in order to demonstrate what the electric potential looks like around a positive charge. So the electric potential around a positive charge is KQ over R. Well, the shape of a speaker cone is such that, and you may recognize it from one of those things you put your coins in from the planetarium and it circles around, right? Well, it's called the potential well, and whether it's gravity or electrostatics, it's the same. It's a 1 over R relationship. So if you actually look at the speaker cone edge on, that is a 1 over X graph that you're looking at right now. That's a reciprocal graph. And so what I do is I say, okay, well, this is from a positive charge, and I got this just from some Sound Store or Radio Shack, if that even exists in the future when you all are watching this. Okay, so and then I say, well, notice what happens. We have a marble here, and that's like another positive charge. So we have a big positive charge that was represented right here. And this marble, it always rolls away, rolls downhill, rolls away. Oh boy, I gotta catch it. I gotta save the marble. All right, I caught it. Oh, good job for me. All right, but you get the idea. And so I tell students, I want you to imagine lines pointing in the direction that the marble goes when it's released. And all those lines would radiate out from the center. Well, in Physics C, we would call these electric field lines, but in Physics 2, we have to talk about vectors, but these would represent vectors that all point directly downhill and away from that charge in the middle. And then I want students to imagine that maybe I could take these lines right here and put them all at the same height. So every part of this little string is supposed to be at the same height. Every single atom of the string is at the same height. Now this string, all these atoms are at the same height, but not the same height as the other string. So each time I add a string, every single one of the atoms of that string are supposed to be at the same height. Doesn't exactly work because they're not perfect. Might need to iron them out or who knows what. But hopefully students will say, well, wait a minute, because of the circular shape of the cone, you make circles. Every point on a circle has the same height. And so those are like the isolines of electric potential, and then you can explain that the isolines of electric potential are perpendicular to the vectors that point in the direction of the electric field. And when the cone is steeper, when the electric potential is steeper, steeper electric potential is stronger electric field. So we have stronger electric field close to the cone, weaker electric field far from the cone. Now, this is the electric potential created by a positive charge. The electric potential created by a negative charge, just the same thing, but turned over. So this would be the electric field created by a negative charge. So let's see what a positive marble would do around a negative charge. Just have a look there. Yeah, we like that. Isn't that fun? Yeah, so there you go. That's what happens in classical mechanics. All right, this is a clipboard, and let me tell you something. Students really struggle with parallel plates, like where one plate is positive and the other one's negative. Well, here's what I'm going to tell you. In my mind, parallel plates are just like a ramp for charges. So the positive plate is like the end of the ramp that's high, and the negative plate is like the end of the ramp that's low. So if this is a positive charge and this is a positive plate and that's a negative plate, then the positive charge feels a constant uniform force, and the positive charge has a constant acceleration as it goes down the incline. So positive plate, negative plate. And then you can even justify this. Now the top is positive, the bottom's negative, and what would a positive charge do between parallel plates if I shot it at an angle and this is the positive plate and down here is the negative plate? It would do a little projectile motion, of course. And so this is an opportunity to talk a little bit about the projectile motion of charges between parallel plates, which is what they've asked that like 3 times in 3 years on the Physics 2 exam. So it's gonna be there. Now, what else do I want students to know? I want them to know a couple more things. If you make the potential difference, that's like the height difference, because electric potential is like height. If you make the potential difference more, then the slope, which is the electric field, increases. However, what's another way that you can make the electric field greater? Not by making the slope greater, not by making the potential difference greater, keep the height difference the same, but just make the plates closer together. So you'll see that between these blocks and my hand down here, the blocks are the positive plate, my hand is the negative plate. When I put them close together, I made the run less. The rise is the same, the potential difference is the same, but the run is less. That's a steeper slope. Or I could take, I don't know, maybe this meter stick, which is much longer than the clipboard. Again, it's the same potential difference, it's the same height difference between 3 blocks on the table, but it is not nearly as much electric field. However, I would want students to know that the amount of energy picked up by the marble is the same whether it goes from 3 blocks to the table on this long ramp, or maybe the marble goes from 3 blocks high to the table on this short ramp. The marble picks up the same velocity and kinetic energy because the same mg height turned into the same 1/2 mv squared. The same way, the potential difference is what determines how fast a charge goes once it passes from one parallel plate to another. It is not the separation of the plates or the electric field. So I would use these analogies all the time in order to help your students understand the abstract of electric field and electric potential. All right, good luck everyone. I'll see you on the next video part C.